A positive integer n with n greater than 3 is called a Nella number if there exists a positive integer x with x less than n, and there exists a positive integer m such that m is not divisible by x or by x plus 1, and m is divisible by every other positive integer between 1 and n inclusive. For example, n equals 7 is a Nella number. How many Nella numbers n are there with n between 50 and 2017 inclusive? First thing is, let's try to understand why n equals 7 is indeed a Nella number. Well, we have to look at all the integers that are in that range from 1 to n inclusive. And then we have to try to figure out an m such that when you divide it by every number in that range, it's going to result in an integer except x and x plus 1. Okay, so that basically means that m divided by x is a no in terms of divisibility. M divided by x plus 1 is a no. But m divided by all of the other integers, all other from 1 to n inclusive, that is a yes. Okay, well, it sounds to me like there's a lot of prime factorization going to be done in this question. That's going to be 2 times 2, 2 times 3, so we have to fiddle around with this. Okay, and after you put some thought, you come to the conclusion that if m is equal to 42 and x is equal to 4, this is going to be why this is a Nella number. So for example, m is 42, right? So 42 divided by 4, that is a no. It's not divisible. How about m divided by x plus 1? 42 divided by 5 is also a no. But 42 can be divided by all the other guys, which are 1, 2, 3, 6, and 7. So basically, we had to find the least common multiple of 1, 2, 3, 6, 7. And that was how I got 42. It was basically the LCM, which is 2 times 3 times 7, which is 42. Least common multiple. All right, so I hope that makes sense. You have to understand the question before we actually tackle this whole big monster there. So when you, after some analysis, you can conclude 2 very important rules. The first rule is that x and x plus 1 are going to be either a power of 2 or a power of a prime. So either they're going to be powers of 2 or the power of a prime. So for example, in our little scenario up here, if you noticed x was equal to 4, which is indeed a power of 2, it's 2 squared, and x plus 1 was 5, which is a power of a prime. Well, it's just 5 to the power of 1. The second conclusion is that n is smaller than the next power of 2, because they told you in the question that x is less than n. So for example, x in our little scenario up here was 4, and that's got to be less than 7, which is what n was up here. And obviously n is smaller than the next power of 2. The next power of 2 would be 2 to the power of 3, since that was 2 to the power of 2, and 2 to the power of 3 is 8. So this inequality must hold true. And these are the 2 rules that we need to abide by to solve this question. So now we have to create a table and look at all the values of n from 50 to 2017 inclusive, and keeping in mind that these rules will help us narrow it down. So here's the values of n all the way broken down by powers of 2, right? 2 to the power of something has to be the endpoint of the range. And then n, as we have said, has to be smaller than the next power of 2. So the largest power of 2 less than n is listed here in this column. And then we have listed x and x plus 1 because x has to be less than n, and x and x plus 1 obviously are consecutive integers. And in this scenario, we have made x a power of 2, so 2 to the power of something, and then x plus 1 is just the number after it. In the other scenario, we'll make x plus 1 the power of 2, and so on. So if you look at this table, we have to conclude that does this work or not? If x is a power of 2, well, that's how we made it. That's no problem. But what about x plus 1? X plus 1 has to be a power of a prime. One has to be a power of 2. The other has to be a power of a prime. Which ones are a power of prime? This one is not a prime. Neither is this one, neither is this one. This one is a prime. This one is not. This one is not. So the only scenario in which x is a power of 2 and x plus 1 is the power of a prime, say q to the power of something, where q is a prime number, is this one. So this is the only range that we have to be concerned with. All the others fail. So all of these guys fail here. Okay, so 257 is less than n is less than 512. And for all of these, we have to see if we can find some m that when you divide it by 256, this guy, which is x, and when you divide it by 257, which is x plus 1, it is not divisible. So no and no. But it is divisible by every other n, from 1 to all the way up until n, inclusive. So when we look at that, we realize the following, that 512 obviously has to go, because if 512 is n, then that means that m would have 512 in it. And if m contains 512, then this would be divisible. 512 divided by 256 is 2. So that one goes. And therefore, n is going to be between 511 and 257. Those are the only ones. So all these integers will be valid. So that's what, 511 minus 256. And that is equal to 255. So that is the first of the values. So we got 255. Now we want to create the same table again, but this time reversing x and x plus 1. So here we go. The ranges are the same, but this time we're looking at the powers of 2 as x plus 1. So this time these are 2 to the power of whatever, p, let's say. And therefore, we have to see if this is a prime or not. Is it some prime q to the power of something? Okay, when we look at these numbers, this is a prime, and that's it. Those are the only two. So that means we are only going to be concerned with that range and that range. Looking at the first range, n is between 50 and 63. Okay, well, first of all, how many numbers are there? 63 minus 49, that's 14. Okay, now all of these valid. Well, in order for them to be valid, m divided by x plus x, which is 31, and m divided by 32, some m. This is a no and this is a no, not divisible. But m divided by all the other guys, all other, from 1 to n inclusive, that would be a yes in terms of divisibility. Okay, well, most of these 14 are okay, but there's two that are not. And those are 62 and 63. And let me explain why. These cannot be Nella numbers, not Nella. And the reason is because if you were to make them Nella numbers, then the M that you create would contain 62. For example, if it's 62, 62 would be part of the product. The only thing that's not part of the product is the x and x plus 1, correct? So 32 and 31 are the only two that are not. So M would contain 62. If n is equal to 62 or 63. And if that's the case, then this m would be divisible by 31, since there's 62 would be in there somewhere in that product, and of course that's not allowed. So we have to subtract these two from this 14. So the total number is actually 14 minus that 2, which is 12. So 12 is the answer to that. Now we get to our final scenario, which is this guy, which is n is between 128 and 255. Well, how many numbers are there? 255 minus 127, and that's 128. Okay, now are all of these valid? And the answer is no, because when n is equal to 254 or 255, that's going to be a problem, because our m cannot be divisible by x, which in this case is 127 right here, and our m cannot be divisible by 128 right there. But if n equals 254 or 255, m would contain 254. And therefore this would become divisible. So that's a problem. So from this 128, we actually have to subtract these two guys. So it'd be 128 minus 2 is at the actual number, and that is 126. So there we go. We got this 255, we got this 12, and we got this 126. So 255 plus 12 plus 126, and that is 393 for this very challenging question, and that would mean the answer for number 25 is A. The number 2018 is used to create the six-digit positive integers. These six-digit integers must contain the digits 2018 together and in this order. For example, 720186 is allowed, but 209318 and 210893 are not. How many of these six-digit integers are divisible by 9? Our integer is going to be of the form 2018 and then something, so xy. Or the 2018 could be in the middle, like that, and then you'd have x and y. Or it could be at the end, 2018, and then you got an x and a y. So these are the three forms. Those are the only three forms, because you can't break up the 2018. Now, here's something that definitely helps with the question, that if a number is divisible by 9, the sum of the digits are also going to be divisible by 9. And that really helps if you can understand that, and if you know that. All right, so the sum of the digits would be 2 plus 0 plus 1 plus 8 plus x plus y. And that is 11 plus x plus y. And this has to be divisible by 9. Well, what are the ways it could be divisible by 9? This must equal either 18 or 27. And I think that's it. Those are the only ways. Because remember, x and y are just digits, right? So x can be between 0 and 9, and y is also between 0 and 9. So you can't get anything bigger. The largest, if they were both 9s, it would be 9 plus 9, which is 18, plus 11, which is 29. So the maximum it can be is 29, that sum. Okay, so let's figure this out. Let's figure it out for 18, and then let's figure it out for 27, and then see what we get. Then we'll revisit, because I think some of these will be invalid, because you can't put a 0 as the first digit, because that would no longer be a 6-digit number. Okay, let's figure this out. First for 18. If x plus y plus 11 is 18, what are our values for x and y? Well, 0 and 7, 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1, and 7 and 0. These would work. And if x plus y plus 11 is 27, that would mean we have, let's see here, 16 would be x plus y, so the only ways are 9, 7, 8, 8, and 9, 7, like that. Okay, so now let's go back and revisit these guys. If x, we're looking at these, I can put 1, 2, 3, 4, 5, 6, 7, 8 different sets for x and y here. But here, the next one though, I can't put this guy. I can't put 0 as the lead-off number. So I can only put these, which are 7. And same thing here, I can't put 0, so I can only put 7. Now let's talk about this. 3, I can put all 3 of these, would work. And there's no 0 problem here, because none of these are zeros, so you can put all 3 here and all 3 here. So now I just got to add up all these guys. So that's going to be 9 plus 8, which is 17, plus 14, which is 31. So 31 different ways of making those numbers. So number 24, the answer is C. What is the sum of all numbers q, which can be written in the form q is equal to a over b, where a and b are positive integers with b less than or equal to 10, and for which there are exactly 19 integers n that satisfy root q is less than n less than q. Let's first concentrate on this inequality. We have n is less than q, and n is greater than the square root of q. We have to do a little bit of fiddling around with the numbers, and when you do, eventually you will get one very obvious solution, that n and 25 for q match perfectly. And like I said, this comes with trial and error, but it would come pretty quickly. There isn't that much of a variation. If you started with 100, you quickly realize that way too many. If you started with, say, 5 for q, way too less. So eventually you'd be able to get this. That means that n is less than 25, greater than 5. So n, since it's an integer, it would be either 6, 7, and so on, ... until 24. And this is indeed 19 integers. So it fits perfectly. 19 integers that satisfy that inequality. Now, my question is this the only value for q? Well, that's the key to the question. The answer is no. We've got to keep fiddling around. All right, what about if n is, say, 24? Square root of 24. Q, I should say. Well, square root of 24 is approximately 4.9, and this means that n is going to be either 5, 6, ... all the way until 23. Well, again, we have 19 integers, 23 minus 4. Perfect. So I got another value for q. Let me write my q values up here. 25, 24. Can I get any more? Well, let's see. How about if I tried 23 for q? When I do, I get the following. I would get about 4.8 less than n less than 23. And that means n is equal to 5, 6, ... until 22. And then now this is 22 minus 4, which is 18. So that doesn't satisfy. So you're tempted to sort of say, okay, these are the only two. But that's the challenging part of the question. There's actually more values because q is not an integer. They specifically say it's just a number. So because it's a number, it could be something like 23 point something. And that is the challenging part of the question. So let's say n is 23 point something. Let's say it's 23.01, just a little bit more than 23. Let's see what happens. 23.01 square root. Well, this is again about 4.8, and this is 23.01. And that means n can be 5, 6, 7, and so on, all the way up until 23. So now I've got 23 minus 4, 19. That satisfies. So when you start playing around with these different values, and that takes a little bit of time itself, you will see that q is equal to 25, that works. Q is equal to 24, that works. But also q anywhere between 24 and 23, that will also work. Any value that is greater than 23, not equal to 23, because we proved that when q is equal to 23, it doesn't work. So it has to be greater than 23, but it has to be less than or equal to 24. Okay, so we've got our q's established. So now we can move on to the next part of the question, that q is equal to a over b. A and b are positive integers, and b is less than or equal to 10. So let's establish what we have. Q is either 25, Q is either 24, but we have a range for Q. It's between 24, less than or equal to, but only greater than 23. And Q is written as A over B, where B is 1 or 2 or 3, all the way up until 10 integers. All right, so let's work with this. The first one, Q equals 25, not much we can do. It's already in sort of a integer format. So Q equals 25, we leave alone. So I'll just write here Q equals 25. Q equals 24, same thing. It's already an integer. Not much we can do. No need to even bother with this. But all the other values that are between, say, 24 and 23, those have to be represented in this form. So that is what we have to do now. So make a little table here. So these are my values for B, and here I will put the unique forms A over B for any number that is in this range. So we have to make these now. Well, when B equals 1, as I said, it doesn't really make any sense. We sort of have, I guess, 25 over 1, if you really wanted to write them out, 24 over 1, but that's about it. 23 over 1 doesn't work because Q is greater than 23. It doesn't equal 23. So we can write them in for B equals 1. When B equals 2, well, we can write now any value that falls in there. Remember, unique. It cannot be duplicated. It can't be written twice. So unique 47 over 2, that will work. And I think that's it for B equals 2. And just in brackets, I'm going to write what it is as a mixed fraction. I won't do it for everyone, just for a few, just so that you know that this is indeed between 23 and 24. When B equals 3, again, the key here is don't put any doubles. 70 over 3, 71 over 3. And in brackets, I'm just going to put what they're equivalent to as a mixed fraction, 23 and 1/3. And this one is 23 and 2/3. So again, these are indeed in that range. So you got to keep going like this. For 4, it would be 93 over 4 and 95 over 4. So this is a perfect example of how I skipped one. I skipped 94 over 4. Why? Because that's the same as 37 over 2. And 37 is right here, if that was written properly. Maybe some of you noticed that. All right, so this one can't be written because it's a double, right? So we got to get rid of that one. Remember, you have to put unique ones because otherwise you'll get too high of a number. And one last time, I'm just going to write in the mixed fraction. I'm not going to do it for every single one. This is 23 and 1/4. And 95 over 4 is 23 and 3/4. Okay. All right, so you get the hang of it. So now I'll just list them all. For 5, 116 over 5. 117 over 5. 118 over 5. And 119 over 5. For b equals 6, 139 over 6, and 143 over 6. Skipped a few because those are doubles when you reduce them to lowest terms. When it's 7, you get a whole bunch. 162 over 7, 163 over 7, 164 over 7, 165 over 7, 166 over 7, 167 over 7. 8. 185 over 8, 187 over 8, 189 over 8, and 191 over 8. You skipped a few because those are doubles when reduced. 9. 9, you get a whole bunch. You get 208, 209, 211, 212, 214, and 215. All of these, of course, being over 9. And finally, for b equals 10, you'll get 231, 233, 237, and 239. And that will all be over 10. So how many do we have? I'm just going to count the ones that are from here to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. All right, 31. These guys. There's 31 of them. Now I've got pretty much to add them all up. I've got to add up pretty much everything in this whole table. Time consuming, but the good news is a quick way of doing it. The first thing, of course, is to add these two. That's easy. 25 plus 24. Okay, so 25 plus 24. So this is the sum of all the possible values of q. Now these guys, these 31, every one of them is 23 point something. As you can see, that's why I wrote some of these in mixed fractions so you can see. Every one of them is 23 point something. And you can also be sure of that because they're all between 23 and 24. So since there's 31 of them, it'd be 31 times 23 for sure. But then you have to add up all of the fractional parts. For example, this gives me a half. But then the good news is for all the other ones, they always add up to 1. You see 1/3 and 2/3 add up to 1. 1/4 and 3/4 add up to 1. And if you were to put all of these in mixed fractions, you'll see that the fractional parts all add up to 1. So you'll get fractional parts adding up to 1 for each pair. So for these, there's 30 of them. There's 15 pairs, and each of those pairs, the fractional part would add up to 1. So 15 pairs, each of them has fractions that add up to 1. So that's just a shortcut. I think it is easier than to manually add up all these fractions. So let's see, this gives me 728 and a half plus 24 plus 25, which is 49. So the total, grand total is 777.5. And that is the sum of all values of q. So number 24, the answer is C. Suppose that 2009 over 2014 plus 2019 over n equal a over b, where a and b and n are positive integers with a over b in lowest terms. What is the sum of the digits of the smallest positive integer n for which a is a multiple of 1004? 2009 over 2004 plus 2019 over n is equal to a over b. Let's add this fraction. So I have 2009 n plus 2014 times 2019 over 2014 n is equal to a over b. Now, since a over b is in lowest terms, we can conclude that the numerators, which are 2009n plus 2014 times 2019, is equal to some sort of multiple of a times k, let's say, and the denominator, 2014n, is also some multiple of b, and that's why when you were to put the numerator over the denominator, they would be equal. So that is our first conclusion that we can make, and hopefully this will help us in the long run. They tell me that a is a multiple of 1004. Well, if that's true, and ak is equal to this whole thing, then that means this part must also be a multiple of 1004. So essentially what we can do is just write that expression as a multiple of 2004. So whatever letter you'd like to use, 1004 times m, let's say. Okay? All right, so this is a basic sort of beginning to this question. Now let's work with this expression right here. Let's multiply it out. So it's 2009, and then when you multiply 2014 times 2019, you get 4066266. Now it is some multiple of 1004. Okay, so I've got to make it look like that. Okay, well, I think I can do that if I break things up a little bit. This 2009, I'm going to break up into 2008 and n. And this 4066266, I'm going to break up into some multiple of 1004 and whatever is remaining. And I can do that as follows: 4066200 plus 66. If I do that, I'll be able to factor out a 1004 from this to make it consistent with the fact that it's a multiple of 1004. 1004 divided by 2000 into 2008n would give me 2n. And then this number, if I divide that by 1004, I get 4050. And then I've got this 66 plus n left over. So at this point, you can conclude that this is obviously in the form that we want, right? This form. But this isn't. So that means the only way this could be a multiple of 1004 is if this is a multiple of 1004. We need to have 66 plus n to be a multiple of 1004 for this to be valid, for this to work out. What that really means is that 66 plus n is 1004 times some letter, let's just say k. All right, so isolating for n, it's 1004k minus 66. So this is basically the form that n is in. We still don't know what is the actual value of n, but that's the form that it's in. Okay, that's pretty good. Now all we have to do is sort of fiddle around with this and see what we get for n. So let's start with the basic one, k equals 1. When k equals 1, n will be 1004 minus 66, which is 988. 238. What we have to show now is this n chosen in a way that it makes the value of a multiple of 1004, which is the criteria of the question. Okay, let's see. For 938, let's see what a over b becomes. Well, remember, it was 2009n plus that 2014 times 2019 divided by 2014n. When you substitute n is equal to 938 and you multiply it all out, you get 5950708 over 1889132. Now, they told me that this is in lowest terms, so I'm going to try to get it close, not necessarily in lowest terms, but at least try to see what I can do. If I divide top and bottom by 4, because both of these look like they can be divisible by 4, I get 1487677 472283. Now, regardless of whether this is in lowest terms or not, at this point I can test it. I can see this is my candidate for A. Is this divisible by 1004? Is it a multiple of 1004? And the answer is no. When you take this number and divide by 1004, you do not get an integer. So, A is not a multiple of 1004 here. Okay, no problem. Let's keep going. This one was for k equals 1, so let's try for k equals 2 this time. When you substitute k equals 2 into here, we get n is equal to 1004 times 2 minus 66, which is going to give me a value of 1942. Okay, so now let's figure out our a over b. Same thing, substitute n into that, and when you do and you multiply it all out, you get 7967744 over 3911188. Let's divide through as much as we can to get it in not necessarily lowest terms, but lower terms. And when you do, you get 1991936 and 9777797. Now let's test it out. Let's take this number, which is my candidate for A, and let's divide by 1004. And it works out. This number is basically 1984 times 1004. And also, interestingly, this fraction is in lowest terms. So that really strengthens our argument that this is our number for n. And therefore, since we have found our n, now we have to find the sum of the digits of n. And that would be obviously just 1 plus 9 plus 4 plus 2, which is equal to 16. So that means that number 25, the answer is A. For any real number x, x bracket denotes the largest integer less than or equal to x. For example, 4.2 bracket is equal to 4, 0.9 bracket is equal to 0. If s is the sum of all integers k, with k between 1 and 999,999 inclusive, and for which k is divisible by the square root of k bracket, then s equals. What we need to do is make a table and see if that table gives us some sort of pattern. And hopefully the pattern will come sooner rather than later. Here we go. So I'm not going to bore you to death by talking you through every single one. This calculation is fairly straightforward. So I'm just going to put in the values. So if it's 1, it'll be 1. If it's 2, it'll be 2, and so on. But I encourage you to make this table, and when you do, you'll be able to, I'm confident, be able to find a pattern. So let's fill it in and let's then talk about it. All right, so just in case you're wondering what I'm doing, let's just illustrate for a couple. When k is 9, basically following this formula, k over the square root of k bracket. So when k is 9, it'd be 9 over the square root of k bracket. 9 over the square root of 9 is 3, and therefore that's just 9 over 3. And that's why that's equal to 3, right there. Let's do it now for 10. When 10 is equal to k, you get 10 over the square root of 10 bracket, and that's 10. Square root of 10 is approximately 3 point something. I don't know what is it, 3.1 maybe. So when you take the bracket of that, it's just 3. So that's how you got 10 over 3. Okay, so it's nothing earth-shattering. And that basically illustrates whether k is divisible by the square root of k bracket or not. And if it's an integer, it is. If it's not an integer, then I will circle them, because those ones we will not include in our sum. The sum is only those for which k is divisible by the square root of k bracket. And those ones are, for example, the ones that are integers, like that. So that's how we will make this table. So here we go. Let's just keep going. Okay, so it's all filled out. I did it until 50. So now what we do is let's circle the ones that we are not going to be using. The ones that this showed that it's not divisible. It gave a non-integer value. And then once those are gone, eliminated, let's look at the remaining ones and see if the remaining ones show us any kind of pattern. All right, so these ones are all gone. There we go. Okay, so what's left? The first few over here, in my opinion, doesn't really give much of a pattern, nothing really consistent. I like coming in from the other end. When I look at it from the other end, it's a little bit more clearer. It's clear to me because that's a perfect square. That's a perfect square. So is that. So is that. So is that. And so is that. And then watch. Before each perfect square, it looks like there's another one that works. You see that? So 36 and then one before it, 25 and the one before it, 16 and the one before it, 9 and the one before it, 4 and the one before it. So that's pretty good, okay? So I think, I'm going to write it down here, that numbers that are of the form m squared, perfect squared, and then 1 before it, m squared minus 1. Okay, but I still got a few more that haven't been circled. So for example, 42, or 30, or 20, or 12. What kind of a formula do I make for those? And after thinking about it for a little bit, it looks like those ones are m squared minus m. Yeah, because this is going to be 7 squared minus 7, 6 squared minus 6. Yeah, that'll work. 5 squared minus 5, and so on. Okay, so these are my forms. Let's test this out. So I think I sort of verbally tested it out. Let's say when m is 5, this will be 25, this will be 24, and this will be 25 minus 5, which is 20. Yep, 25, 24, and 20. And similarly for all the values, it will work. Okay, great. I got a pattern. So all the k's are of these forms. Now, we are going from 1 all the way up until, well, not 50. We're going up a lot higher than that. We're going to this 99999 number. All right. So that means that if this is my m squared, I've got to figure out what is m. So I'll just do it on the side here. M squared, the highest it can go up to is this. So when I take the square root, I get m is equal to 999 point something, but I've got to use integer values because they were clear that they're all integers. All right. So that means my sum, S, is basically all the sums from m going from 1 to 999 of these three guys. So m squared plus m squared minus 1 plus m squared minus m. And that's it. So if I can figure out that, I'll be in business. And then at the end, I'll just double check to see if I've done this properly. Okay, so let's combine this before I make the summation. M from 1 to 999. I can combine 3m squared minus m minus 1 like that. And then I can break it up 3m going from 1 to 999 for m squared minus the sum from m going from 1 to 999 of m, and then minus the sum from m equals 1 to 999 of 1. Okay, well, this is where some of those formulas come in. One of these formulas you guys know. This one, most people will remember. 1 plus 2 plus 3 plus ... all the way until m is equal to m times m plus 1 over 2. But the other one, which is 1 squared plus 2 squared plus 3 squared ... the sum of the squares, that's a lesser known formula. Some of you remember it, some of you don't. I'll tell you what it is. It's m times m plus 1 times 2m plus 1 all over 6. All right, so that's what you're going to use. Okay, I think we're making some excellent progress here. So let's use this one now. Using this formula here, it would be 999 times 999 plus 1, which is 1,000, times 2 times 999 plus 1. So times 2 times 999 plus 1 all over 6. Okay, now let's do this guy. That is going to be minus, that's this formula over here. So that's 999 times 1,000 divided by 2. And then this one is just the sum of 999 ones. So that's just minus 999. And that's it. Okay, great. Now let's do this number crunching. 3 times 332833500 minus 499,500 minus 999. And this whole thing becomes 998,000,001. 998,000,001. Okay, let's go back and look at the answer choices. That number was 998,000,001. It's not one of the answer choices. And I'm happy that it's not, because if it was, I would have circled it and moved on. Because that is incomplete. We've done everything right so far, but there's 2 numbers we're missing. So, okay, well, I don't understand. Why would we be missing anything? Well, here's the story. Everything we've done so far is perfect. But we only went up to 999 for m, which is fine because that's what the limit was. But let's say m is 1,000. Let's see if we can squeeze in a few more numbers. If m is 1,000, what's m squared? Well, that's a million, right? Okay. What about m? This guy right here. The first one, m squared. The next one is m squared minus 1. Well, m squared minus 1 would be 999,999, like that. And then what about this guy? M squared minus m, when m is 1,000. It would be 999,000. Now what we have to do is see if any of these numbers fall within our range. And remember, our range was right here between 1 and 999,999. Okay, well, the range was M or K, whatever letter you want to use, between these two numbers. Well, this is not, but this is, and so is this. So that means these two numbers I've got to also include in my sum. So no problem. The sum that we calculated, add the 999, 999, and also add the 999,000. Those are the only two additional numbers that we need to include. And when you add up these three, you get 999,999,000. And that is indeed one of the answer choices. 999,999,000 is choice C for this great question, number 24.